Hello everyone. We're going to work another AC circuit analysis problem, and before you watch this one you should watch the previous videos on AC circuits, complex impedances, and phase relationships. Okay, so now in this problem we are to find the phasor voltage V. That's right here, and that appears right here. That's across the current source, and we're supposed to find the phasor current. So the total current going in, the phasor current in the resistor, phasor current in the inductor, phasor current in the capacitor. And this is interesting. We want to find the phasor current going in to the inductor and the capacitor. Okay, so we're going to be looking at this part of the circuit, considering it as a whole, and you can see by the name I-tank, this is actually referred to as a tank circuit in here. Okay, so this is an AC circuit analysis problem, and we need to use our tools to be able to solve for this. Okay, so now what are the things that we can observe? So now if you look at the problem, we can see that the impedances for the inductor and the capacitor are given to us. So they're not given as 5 millihenries and 1,000 microfarads or anything like that. It's given in terms of the complex impedances. Okay, but that means that we do not have to use the radian frequency, which appears in the argument of the sinusoidal function in the driving source. Okay, but let's just say we wanted to calculate the values for those components anyway. So if we wanted to find out what L is, we know that the complex impedance of ZL is J200. And we know that ZL is equal to J omega L. So we know what omega is, we know what ZL is, and then we can solve for L. Okay, and then this simple calculation gives us a value of 200 millihenries. So if we want to find the actual value for the inductor, this is how we could do it. Okay, and then we could do the similar analysis to solve for ZC. We know that ZC is minus J200, and we know the equation for ZC is 1 over J omega C. And by plugging in the numbers and solving for the capacitance, we can find out that that is 5 microfarads. Okay, so we know we can easily find the values given these parameters in the circuit. Okay, if we want to find that. Okay, so that's one thing we observed about the impedances, and another thing that we can observe is that if we're going to use node voltage analysis, we can just use the V here to denote the node voltage. Okay, this circuit is in parallel, so those two V's, the complex phasor or the phasor voltage, is the same in both those cases. Okay, so we can simplify our notation a little bit. So now let's think of a conceptual question. We see that the phasor voltage is denoted with a polarity. Okay, and so does this matter? Okay, so we looked at this a little bit in the previous video, but now this is what we have here. This is the case that we have here with the polarity denoted plus minus in this direction, and we have the phasor voltage. Now if we translate it by flipping the polarity, then what we have to do is flip the sign. Okay, and so this now it becomes equivalent, and you can look at the previous video that we made on AC circuit analysis to see the discussion between the difference between a voltage phasor V and minus V. Okay, so now let's get started solving this circuit. So when we're doing AC circuit analysis, we have to convert everything to phasors and complex impedances. Okay, so now what we will do is convert I of t into a phasor. Okay, so we have that right here, and then we do the method that we saw before. We bring down the magnitude, okay, and then bring down the phase, which there was no phase in the argument, so it's 0. And then we note that omega, so that was omega, that disappears in the phasor representation. It doesn't, we can bring it back later if we need to, when we're going back into the time domain, but when we convert to phasor form, omega just drops out. So then we can write that phasor current, the total phasor current going into the circuit, up here. So we'll denote it on our drawing. Okay, so then we could use node voltage analysis to find the voltage, okay? And so we're solving for the node voltage at this point up here. It's a parallel circuit, so the voltage is the same for all circuit elements, okay? So then we do our circuit analysis exactly the same way that we would do it in DC circuits. So we have the current going to the left, okay, and we had found that as 0.01, and we use a negative sign because the arrow is pointing in the opposite direction, okay? And then we can go the other direction, okay? We can go down, and we see that we have the voltage on one side, on the top, as V, and it's going to the ground reference node. So it's just going through this impedance, okay? And that's what appears down here, 1000 ohms, okay? And then we repeat the same method for all of the currents going down. So this is the current down through the inductor. The impedance is J200, and then we look at the phasor current going through the capacitor, and so its impedance is minus J200, okay? And it has to equal to 0. Okay, so that's fairly straightforward. So now we're just going to do some manipulations. So we're going to multiply by 1000 to simplify the denominator. And so let's just take a look, just make sure that you understand how to do the manipulation. So here, how do we deal with the minus J200 when we multiply by 1000? Okay, so this is the operation that we're doing to get to the next step. Okay, and what we want to do is we want to take this J upstairs, right? So J goes upstairs like what we have here. And when we take J from the bottom, from the denominator up to the top, we flip its sign, okay? So that's why the negative sign disappeared, okay? So that's just illustrating to you what's happening. So then you see the result over here. So that should be clear to you. And if it's not, then you gotta go back to the basics and make sure that you understand how these operations work, okay? Because that's a really fundamental operation for us. So then we can notice that, you know, these two terms are equal and opposite, and so they work out to 0. So we can easily find the phasor voltage as being equal to 10. Okay? And then we can plop that into our diagram to record it. Okay? And then we're going to use Ohm's law right here to calculate the branch currents, okay? So now, for phasor current through the resistor, we are going to use Ohm's law, so it's just the voltage divided by the resistance, okay? I is equal to V divided by R. So we plug in our values, and we get a phasor current of 0.01 amps, okay? And then we're going to repeat the process for all the other branch currents. So we're going to do phasor current for the inductor. Okay, and then it's just I divided by Z. Okay, so this is the more general version of Ohm's law. So we put in our values here and then calculate, and we get the phasor form 0.05 with a phase angle of minus 90 degrees. Okay, the minus 90 is coming from the minus J. It's a value that resides purely on the negative imaginary axis, and that's why we have minus 90. And then when we do the phasor current for the capacitor here, then it's again voltage divided by impedance, plug in the values, and then calculate, and we get 0.05 with a phase angle of plus 90 degrees. So that's interesting. So now we're going to do something pretty tricky and pretty awesome. So I don't know if you've come across this before, but you know how we do KCL. So imagine that we're doing KCL on this node, right? And we say all of the currents in that node have to sum to 0, okay? So what goes in is equal to what goes out of that node. But we can also use the KCL concept at a connection point, okay? And in this case, we're using connection point A. So that's this guy right here, okay? So then we can say the current going into that connection point is equal to the current going out of the connection point, okay? And you can see logically that makes sense. So then current leaving A, the connection point A, we've already calculated it, and we said that it's the phasor current for the inductor plus the phasor current for the capacitor, so it's minus J 0.05 amps plus J 0.05 amps. And that is going to work out to 0. So the current flowing into this tank circuit is 0. Okay, so that is super interesting. And what that means is that we could actually remove this circuit and it wouldn't change the voltages or currents in the rest of the circuit because there's no current flowing in to the parallel inductor and capacitor. That's its property. And this property is only satisfied at that frequency, at omega equals 1000. So then, let's just summarize all of the parameters that we found, okay? We have the phasor current going in, we have the phasor voltage across all of the elements, and we have all of the branch currents in phasor form, okay? We've solved for all of them. Okay, so we've done what the question asked, but let's explore a little bit more, and let's just see what those phasors look like on the complex plane, okay? Let's plot them. Let's see what they look like. So I've written out all of the phasor values over on the right-hand side, and we're going to plot it on the complex plane. So let's see what that's going to look like. So this is quite interesting, and it's a little bit mixed, okay? We have currents and we have a voltage as well, okay? But this is just showing the relationships, the phase relationships between them. So one thing that is quite interesting to notice is the phasor current for the capacitor is 0.05 pointing up, and the phasor current for the inductor is 0.05 pointing down. So this is why these currents cancel themselves out. They're in the opposite direction, and that's why the tank current is 0. Okay, and a little bit later we're going to see what it looks like in terms of a voltage waveform. Okay, we also see that there's a phase relationship between voltage and current for the capacitor. So then in a capacitor we have ice. So current leads voltage in a capacitor. So the current is counterclockwise, okay? So it's 90 degrees leading the voltage, okay? And similarly, we can say that current is lagging the voltage in the inductor or what we have is Eli. The voltage leads the current in an inductor. So we can see that relationship there. And another thing that we can notice is right here. The current in the resistor is in phase with the voltage, okay? So that makes sense to us as well. There's no phase difference between voltage and current in a resistor. So let's see what these relationships look like in the time domain. So this is a plot that you can study, and you can take a lot of time studying this, okay? They very deeply understand what's happening. So now let's take a look at phasor current for the capacitor. So that's drawn in red. So that's this guy right here. Okay, and what's its relationship to the phasor current for the inductor? And that is drawn here. And you can see the relationship in the time domain. So they're equal and opposite, okay? And what that means is that, so we can see that the relationship of IC is equal to minus IL, right? And we saw in our earlier lecture that this means that there's a shift of a 180 degrees, either to the left or to the right, between those two waveforms. They're equal, but 180 degrees shifted apart, which you can clearly see from the drawing. And then you can also see the relationship Eli and ICE in the waveforms, okay? So let's look at the inductor waveform. Okay, so let's get rid of the capacitor drawing. So we have the inductor waveform, and let's look at its relationship to the voltage waveform here, okay? So this is the voltage waveform. So for an inductor, voltage leads current by 90 degrees, okay? And we can just see that right here. This point is the current waveform, and the voltage leads it by 90 degrees, okay? So voltage leads current by 90 degrees. And then we can see the converse, okay? Okay, so now in this case, we have ICE. Okay, the current leads the voltage by 90 degrees. So we can see that the current leads the voltage by 90 degrees, okay? So the current is leading by 90 degrees, okay? Okay, so now let's take a look at what's happening with the tank circuit. How can we have zero current going into this part of the circuit, okay? Shouldn't there be some current flowing? Okay, well, let's do an analysis. Let's find the equivalent impedance of this tank circuit, okay? And how do we do that? Well, we use our parallel formula. So it's just the two impedances multiplied together on the top, and then the sum of the two impedances on the bottom. Now, since the impedances were equal but opposite, okay, so then we can see the denominator goes to 0. And then the top is 40,000. And when we resolve this, this is an indeterminate answer, and it basically either goes to positive infinity or negative infinity, okay? And the important thing here is that if this impedance appears as either positive or negative infinity, that means no current is going to flow through it, okay? And it's going to appear as an open circuit. And what's important is that it appears as an open circuit at that frequency of omega is equal to 1000, okay? This condition only applies at that frequency. And this is called parallel resonance, okay? So that the special case is called parallel resonance, and the equation to calculate it is omega naught, so which stands for the resonant frequency, and it's 1 over the square root of L times C. Or if we want it in hertz, we just divide that by 2 pi, okay? And then where does this 1 over root LC come from? Well, for this circuit, we want the magnitude of the inductor's impedance to be equal to the magnitude of the capacitor's impedance. And that is the condition so that the denominator goes to 0. Okay? So then, once we know that, once we have that concept, then we could just plug in what we know about the impedance of the inductor and what we know about the impedance of the capacitor, and we know that at the resonant frequency, ZL has to equal minus ZC. Okay, and then we can bring down those equations and make them equal, okay, with the minus sign, of course. And then, by some very simple manipulations, we can solve for omega naught is equal to 1 over root LC. Okay, and this creates a condition where the Z equivalent goes to plus or minus infinity. Okay, at that resonant frequency omega naught, and that's how we get the open circuit. And this circuit actually is a very, very important circuit. It's beyond the scope of the course to really discuss the applications, but what it is essentially, it's called a tank circuit. It's also called, it's an oscillator, and what it does is it acts as a band pass filter. So it passes intermediate frequencies, well, frequencies at the resonant frequency. Lower frequencies get kind of absorbed by the inductor, and high frequencies get absorbed by the capacitor, and intermediate frequencies pass through, the ones at the resonant frequency. So now, there's also a really interesting application of this LC, but in series. Okay, this is a series LC, and this has a series resonance as well. Okay, but in contrast to the parallel LC, this LC appears as a short circuit at the resonant frequency. Okay, at the series resonant frequency, and we can see that. In series, the equivalent resistance is just going to be ZL plus ZC, and then if the impedances are equal and opposite in magnitude, they're going to cancel each other out, and we're going to get 0 ohms. Okay, so this parallel LC is going to appear as a short circuit. Okay, just wanted to do this a little bit of embellishment just to give you a little bit more understanding of AC circuits beyond just getting magic numbers for, you know, what's a phasor current, what's a phasor voltage, and so forth. And in fact, for this series LC, if you're interested, because of your interest in circuits, you can go and do a analysis like that for the series LC. This is for the parallel LC. Okay, so hope that was useful.